Okay, ready, yeah.
Yep. So I guess we'll start with the blue problems, which are the easier ones. I guess I'll pick an order. I think this would be the correct order. So first is the problem Simon Says, which is pretty straightforward. You're just given a list of strings, and it's like in each line you have to it either starts with Simon Says or it doesn't. If it starts with Simon Says, you should just output the rest of it. Otherwise, you ignore it. So really all it's checking is, can you read a line of input? Whereas normally, like if you just see in a string, then it'll only get to the space separator. So it's basically just checking if you know how to like get the next line of input with your language of choice. In C++, you would say like get line cin string. Or you can also, yeah, I believe this is just the best way.
I wonder whether people actually look at the output and then try to decide whether there's a white space in front of the word.
Yeah, one thing I didn't like about this is I think they should have been a little bit more clear about
Right.
like that white space.
But I downloaded
important.
the sample test to be sure. So
But another thing is like, what if it's like it doesn't really say like what if it's Simon Says, but then there's no space here? Or what if this is lowercase or something?
I guess they said that there has to be another space after Simon Says, but it's just the output, whether they include that space or not, it's not explicitly specified.
So yeah, I think there's too many details that they have to specify in order to do something that's extremely simple. So I didn't really like the problem personally. But anyway, it's important to know how to read a line of input, and we saw that in like some previous practices too, and not just like read in a string until the next white space. So it's just important to be familiar with that. We can move on.
Yeah, I think that's.
Next is 8 queens. So the problem is like there's this classic puzzle where you have like an 8x8 chessboard and you want to know, can you put 8 queens on the board so that no two of them attack each other? And it's just like they move like in chess, so horizontally, vertically, and diagonally. Usually, like it's a standard problem to like count or to find all of the ways to do it or count number of ways. But this problem, it's you're just given 8 queens on the board, and you have to check if the condition is holds. So you just basically need to. So it's a brute force problem. Like the size is only 8x8; it doesn't get bigger. So you just have to be able to check for each pair of queens whether they attack each other. Or another way to do it is check any 2 cells that would be a conflict if both of them had queens, and then just check if they both have queens. So, so what's the condition for when 2 squares would attack each other? So first of all, like let's say that we have ij and maybe I'll use different letters. I'll use XY and I don't know, ZW. Let's say these are the 2 cells. So they would make a conflict if X equals Z. I'm saying like this would be row column. So if they're in the same row, then they attack each other. If Y equals W, they're in the same column and they attack each other. And then there's 2 different diagonals. One of them would be like X plus Y equals Z plus W. And the other diagonal would be X minus Y equals Z minus W. So you can just check like for each pair of queens if like you can identify all the positions of the queens by the positions of the asterisks, and then just check if any of these hold. It's pretty straightforward, I think.
Yeah.
So it's just good to know that like these are the equations of the diagonals. It's just good to know this.
Yeah, I guess I did check sort of using the code similar to how you would generate them, but the code turns out to be a little bit more complicated. So I check every row, there's only one, and then I remember the column it is in, and then whether a column is occupied and whether a diagonal is occupied. So using this brute force check, it's a little bit slower when generating all the configurations, but for this problem, it's have a simpler code.
So if it asked for like a much larger grid, and we had like positions, like we just had a list of coordinates of queens, then like this idea can do it like pretty fast. So like for each queen, you can store like you can have like four different hash maps of like these values, and then so it's like you store its row position, its column position, its first diagonal position, its second diagonal position, and then if any two queens like have the same value in any of these four hash maps, then you have a conflict. So that's how you would solve it on like a much larger grid in like linear n log n time.
Cool.
Let's see what's next. Flexible spaces. So in this problem, we have like this rectangle, or a room, as they say. So it's like the leftmost coordinate is 0 and the rightmost is W, the width of the room. And then there's some dividing lines at different points inside of it. And the question is, what are all of the possible widths of a room if you chose like some of the dividers? So for example, I could make a room of width 7 by adding this divider of 1 and this one at 8. And then 8 minus 1 is 7. So 7 is in this list. But for example, 5 is not, because no matter like which sections you take, you can't get to 5. So an important thing here is that the room has to be connected. So like I can't choose this segment and that segment and then like say that this segment is not part of the room. So once you understand the statement, you really see that the size of the room is really just the rightmost wall minus the leftmost wall of wherever you choose the room to be. So really you want to find all of the differences between two dividers, and you include 0 and the total width. And the constraint is very small, it's like 100. So you can just take each pair of numbers. So like you add 0, you add 10, and then you take each pair and you check their difference and add it to the set. And then you just list them all out in sorted order. So this one's also pretty straightforward.
So this is a digression. It's not just kind of related to this problem. So I'm wondering if you have a size W and you want to create a room of all integer size from 1 to W, then how many divider would you need? So is that this should be some known problem. Do you know the solution out of it?
Like, so trying to do the reverse of this? Like
yeah,
saying,
trying to do reverse, and you want all, let's say you want all integer size possible. So how many divider would you need? So I guess W plus 1 choose 2 would be a bound. So you need at least that, but I suspect that's difficult to construct using just that to get all the size.
I'm not sure of the answer to
Yeah,
that.
yeah. So it's just a random thought while you're explaining it.
If they don't have to be connected, then you just do bit masks. So like you have powers of 2 as the sizes.
I suspect that, yeah, even that might not be optimal because you get to choose two of them. So if you just use from the left bind to the, I don't know. Yeah, it's but yeah,
Mm-hmm.
just interesting math problem.
Yeah, I didn't think this problem was worth talking about too much. It's like when I read it, I thought it was going to ask about like knapsack,
Okay,
but
I see.
instead it
I
was
see.
much simpler because they have
Yeah.
to be connected.
Yeah.
Okay, let's move on to this one. So this problem, you can ignore like most of the statement. Like there's just a lot of story that you have to ignore. But so there's a bunch of characters. Each character speaks a language and they understand that spoken language and also potentially some more. So let's say Boba Fett, he speaks basic, and if someone speaks to him, he will understand languages basic and QTs. So what's the question? It's you want to like keep the largest number of people inside the room, or in other words, like take away the smallest number of characters, so that everyone who remains in the room can converse. And that doesn't mean that it has to be direct. Like, so like let's say person A they speak a language that person B understands, and person B speaks a language that person C understands, then person A can talk to person C, even if A doesn't speak a language that C directly understands. So like any path of translators is like okay. Okay. So part of the problem is just to parse the input and like they don't say how many strings are on the line. So again, you need to like read in the entire line. You can use a string stream to like take each word ignoring spaces, or you can do get line with a delimiter. So after you parse the input, then the input's kind of small. It's 100. So you can actually afford to like add an edge between each two people that can converse. So you can take, so like for each pair of people A and B, you can iterate through all languages B can understand and check if A's spoken language matches one of them. Or you can use a hash map for that. So basically we'll end up with, there are n characters, and we'll have up to of n squared like edges between them. So a directed edge between two people A and B means that A speaks a language that B understands. Okay, so then what is the question in relation to this directed graph? So we want to have a set S of people, so like a subset of the vertices in the graph, so that if A and B are two people in S, then this means there exists a path from A to B. And like A and B can be swapped, so like there also exists a path from B to A. So we want to find the largest set of vertices so that any two vertices in the set, there's a path from A to B and a path from B to A. So this is a pretty standard problem. Like there's this there's a well-known thing called strongly connected components. So I'll start by saying what's strongly connected. So the condition for the set S is what strongly connected means. So we say that a directed graph is strongly connected if for any two vertices, there exists a path from A to B and a path from B to A. So as a warm-up, we can say, how do you check if a given graph is strongly connected? And an easy way would be check for all vertices V. You can do a DFS starting at V and check that all vertices U are visited. And this would give us complexity O of NM, if M is the number of edges. And if it's N squared, then if there's N squared edges, then this would be like N cubed. But this isn't the most efficient way to do it. So the thing to realize is that what if we pick a particular vertex let's pick one vertex. Suppose it can reach everything. We can check that in linear time, like number of edges. So we can check if V can reach everything. We can also check if everything can reach V in linear time. And that is done by just reversing the directions of all the edges. So we reverse the directions of all the edges. And if in this reversed graph, V can reach everything, then that means in the original graph, everything can reach V. So in this example, V can't reach anything actually. But like if there was an edge here, then we could, DFS and see if it can reach everything. So that's how you can check if a graph is strongly connected. You just check that V can reach everything and check that everything can reach V by like doing the same thing, but on the reversed edges graph. Okay, so why is that enough? Like say you have any two vertices, I'll say A and B. Say there's any two vertices A and B. We want to know, is there a path from A to B? Well, clearly we already checked A, and everything can reach V and V can reach everything. So for any two vertices, there's a path between them. And similarly, there's a path from B to V and B to A. So that's how we can check if a graph is strongly connected. And then generalizing from that, there's strongly connected components. So I don't know if I have time to cover everything there, but essentially the idea is that any directed graph vertices so that within each set, it's strongly connected. So like everything can reach everything in here within any of these sets. And then any edges going between the components they don't have cycles. So it's a directed acyclic graph if you only consider the edges like between components. So in order to compute strongly connected components, what's the name of the algorithm? I think the name is blinking me. What was that? Oh yeah. So the name of the algorithm is Kasaraju algorithm. So you can look this up on your own or ask questions later, but I think I don't want to go into detail about how it works. but it solves the problem of strongly connected components in linear time using two depth-first searches. So to solve the actual problem, a strongly connected graph has to be a subset of one of these components, and the largest one will just be one of the actual components. So the answer to the question is the people left in the room should be the largest component, and the number to output is the number that leave the room, so you just say n minus that number. Okay, any other concerns?
Okay. Oh, wow.
So yeah, I think a strongly connected components problem appeared in 2018 in our region, so it could be good to know about that and study on your own, or if you have any questions, then I'll be happy to answer. Okay, for the remaining problems, it looks like H is the easiest. Whoops. Okay, then E, then maybe G, because many people attempted that. Okay. So problem H is we have this grid of numbers. Also, there's so we're interested in paths from the bottom left to the top right, and as we walk, we're only allowed to move right and up, and the cost of doing it is like the sum of numbers on the path that we visit. So, but there's something that's different, which is we have like a sheet of paper that has a list of digits on them. So for example, let's say it's 1, 1. So this means like this is a sequence of like jumps you're allowed to make. So normally you can only move like one cell at a time, but you're also allowed to jump by 1. And then you're also allowed to jump by 1 again. But you're only allowed to do that twice, and you have to do it in like the order that it's given in. So for example, you can start at 1, move to 0, move to 3. Then you can use the first digit and you jump by 1 over to the cell 2. Then you're not allowed to use the first digit anymore, so you move on to the second digit. You can jump over the cell, move to 1, then move to 1 to 8. So basically, like you're allowed to make these sorts of jumps. You have to make them in the order. You don't have to use them all. And once you use one, then you can't use it again. So this is like a shortest path problem. But normally in a shortest path, you only need to care about what state you're at. And the problem here is that there's information about how many digits have you used up so far, and you need to account for that in your shortest path. They say something like the number is guaranteed to be less than 10 to the 50. That can look scary, but you just realize you don't read it like a number, you read it like a string, and the digits are the only things you care about. So it's just a string of 50 digits. The grid size is 100 by 100. So the key thing to realize is you can encode in the state not just the cell you're at, like the cell you're at would be some coordinates x, y. You can also encode how many digits are left on your piece of paper. So for example, I start with 0, 0, 2 because there's two digits left. Or maybe I could say like which digit is next, and then K would be the end, so like an empty paper. So if these are the states, we have all the information about where we are and what we're allowed to do. So we could just ignore the piece of paper and just like move like normal. So we can move right by 1. We can move up by 1. Or we could also take a jump. So like we can use the kth digit of the code. So it would be like code of k. So we jump over that many cells and then we move by 1. And then we're not allowed, we already used the kth one, so we have to advance to the k plus first one. And then similarly, there's this edge here. So it's like a shortest path problem, and these are the states, and these are the edges you're allowed to make. So what's the complexity? There's 100 by 100 by 50 states. So like n is this, m is, there's like 4 edges per vertex, roughly. So it's like a reasonable size graph. And if you use Dijkstra's algorithm, then it should. So Dijkstra's algorithm works for this. But also there's, you can actually do better. So Dijkstra's algorithm has a log in the complexity, but you can actually do it in linear time. So if you have a directed acyclic graph, you can compute shortest paths in linear time with dp. So in this example, it's so x, y, and k, they never decrease on these edges. They only increase. So it's actually a DAG, and you can just do linear dp, which is probably the simplest solution, I think. Any concerns?
Yeah, I guess so. To me, I look at the grid sort of first view at the DP, but it's good to see also it can be viewed as a graph shortest path.
Mm-hmm. So yeah, so I guess that's also another thing that's good to know about, which is like, so like longest path in general is NP complete, but on a DAG you can use DP, and shortest path and longest path like doesn't matter. And negative edges don't matter for shortest path if you have a acyclic graph. So that's good to know about, that you can do DP for shortest paths in an acyclic graph. I also think for this problem, it's simpler than like Dijkstra's algorithm to implement. I guess let's move on to E. So in problem E, we have a tree, and each edge has a requirement to be covered a certain number of times. Like this edge needs to be covered 7 times, this edge 3 times. Is it exactly that much, or at least? I think it's exactly.
Exactly, yeah.
So in order to cover edges, you can have like a unique path between 2 vertices. So like this red edge is the path between 6, 4, 0, 1, 3, or these 2 paths are from 3, 1, 2. So we basically need to have the smallest number of paths to cover every edge the exact number of times that it needs to be covered. So, well, okay, so instead of paths, it says patrollers, but yeah. So it's the minimum number of paths to cover each edge. It's required number of times. Exactly. So I think when I read this problem, like I was like, this looks pretty standard, but I was stuck for a bit. So But there's like a cool observation you can make that makes the problem a lot simpler. So so let's consider another way of counting how many paths there are. Instead of counting how many paths there are, like the total length of all the paths is fixed. It's just the sum of number of times each edge has to be covered. Let's see, what was it like? Let's say there's 2, and there's 7. Let's say 3, 5, and 3. Something like this. So the total length of all of the paths is fixed because it's all of these edges. But really, in order to form a path, we're actually saying we should connect some of these together. Like we should pair them off at the junctions. And if you think about the problem this way, it becomes a lot simpler. Because every time you connect 2 of them, you're decreasing the number of paths by 1. Right? Let's say you connect these. And you will never make a cycle because the overall graph is a tree. So whenever you're connecting 2 endpoints at a junction, you're decreasing the number of paths by 1, and they're always paths. So the fact that every time you connect 2 of them, it decreases by 1 means that you can treat these nodes independently. So let's take the node that was here. It has 7 edges here. It has, what was it? 1 and 2. So we can do it for all nodes independently, and then the total number of paths that we decreased it by will just be the sum for all the work we did for each node. So we can connect 2 endpoints if they come from different nodes. So we can't take these 2 nodes and then connect these together. We are not allowed to do that because that could create a cycle. And also this path isn't, that path is not allowed. So we need to find how many of these endpoints we can pair off. So I'm just gonna say we're focusing on only one node right now. So we have an array 1, 7, 2. So let's say that we have 1 x, 7 y's, and 2 z's, let's say. So we want to match different characters together to minimize the number of pairs. So what we can do is, let's try to get a lower bound, or sorry, an upper bound. So obviously the total number, let's say that there's n of them. So n over 2 is definitely and floored. That's the number, that's the upper bound on the number of pairings we can make. Because if we just ignore characters, that's how many pairings you can make. So this is definitely an upper bound. Another upper bound is considering the maximum number of, the maximum, the most frequent character. Let's call the number of occurrences f. So in this case, it's 7. So all of them must be in distinct pairings. So we can have at most so that also means that everything else, n minus f, there's also at most that many. So there's at most n minus f pairings, I guess. Because each pairing must have one of these characters. If a pairing didn't have any of them, then it would have two y's in this case. So definitely the answer is at most this number, minimum of floor n over 2 and n minus f. And actually the answer is exactly this. So let's see why that is. So what you can do is take this and then rotate it by n over 2. So in this case, n over 2 is 5. So let's rotate it cyclically by that amount. And then we'll consider each pairs of different characters. And that will be our answer. If we actually wanted the construction, we could do this. So why is this the minimum of the two things? So if the most frequent number is less than n over 2, then we would actually get all of them paired off. Wait. Maybe I'm confusing myself. I think we get each pair twice. We're counting each pair twice. Okay, I think the argument doesn't quite work for this case, but it's a similar argument. So I think what the actual best way to do it is say, like, take the maximum occurring number. Let's go back to numbers. We have 1, 2, 7. We pick the maximum 2, we make a pair, we pair them off, and then decrease their numbers by 1. So we could say like 1, 1, 7. So we made one matching. Then we take the maximum 2 again. It'd be 1, 0, 7, or 1, 0. Sorry, I didn't decrease 7 by 1. We match these off. We get 1, 0, 5. Then we take the maximum 2, and we have 0, 0, 4. So
sorry, I was a little bit distracted at the beginning. So the 1, 2, 7 is the 3 edges. 3 edges have 1, 2, 7.
Yes. So vertex 4 here has 1, 2, and 7. So
you look at each vertex one at a time. Or?
Yeah. So we treat each vertex independently, and then we merge like the path endpoints together, and we want to merge as many as possible. Every time you like connect two endpoints together, you decrease the number of paths by 1. So if we have 1, 2, 7, we like we always. So one way to construct like my bound of like n over 2 and n minus most frequent would be like this. We didn't actually need to construct. So in my code, I just did the number. But if you want to understand it, then this is probably the best way. Yeah. So you always decrease the most frequent by 1 in each step, and you always decrease the sum by 2. So it's.
Yeah, so I did it using DFS. So yeah, but I think and this kind of tree with path matching.
Mm-hmm.
It's actually becoming very common the last year or two. There problems doing this like everywhere.
Mm-hmm.
Yeah.
So in my code, I didn't use any DFS at all. So the only important thing is for each node, what are the numbers adjacent to it?
Yeah, I guess the benefit of using DFS is you can be really dumb. So it's like there are you don't have to have much insight. It's more mechanical in some sense. So you root the tree arbitrarily, and then you look at each node, the subtree. You will get something unresolved from each of your children, and then you can use the parent to help you resolve some, but the rest of them you have to resolve yourself by creating the path. You just add those up, and that gets you the answer. So yeah, I'll probably explain that separately, maybe using some other example problem as well, because I think somehow these are really popular. This kind of you can call them tree DP, but essentially you and a lot of these are actually related with decomposing a tree into paths. So
okay, but yeah, I think I talked for a while, but that was my solution.
Yeah.
Okay. I actually think B is easier to understand the solution to, but G might be easier to like code.
Yeah, you can explain B first. Yeah, I think
B is easiest to explain.
Yeah.
So in this problem, we have like an infinite plane, and then we draw some circles, and every time we draw a circle, it erases anything that's strictly inside the circle that was already drawn before. So in this example, say we like draw a small circle, then we draw this big circle encompassing it, then that entire small circle is erased. Or in this case, we draw like this left circle first, then we draw the right circle. So then the boundary of the first circle that was inside the second one that was drawn is erased, but then this edge isn't erased by this first circle because it was drawn after it. So the question is, we have all of these circles that are drawn. We know their position, like the center and the radius of each circle. And the question is, what's the total perimeter, like the total length of everything that's drawn when you're done? So not counting the erased parts. And I guess as one edge case, if you have two circles that are exactly the same, then you don't count the perimeter twice. Okay. So for this problem, it would be enough to say, like if we could know for each circle, what are all of the erased parts of its perimeter? Let's say we know that, let's say that for each future circle, we can find these two intersection points, and we say that this segment is erased. And then for this future circle, we say these are the two intersections, so then this segment is erased. And again, for every circle that comes after it, we suppose that we have all of these segments. I can discuss in more detail like how to compute these segments. But so we're just going to assume that for each circle we have the segments that are erased from future circles. Then the question is, we can afford to do that for each pair of circles if circle intersection is fast enough. Because it's 2000, so we would just be doing n squared work there. So we're just going to suppose we have a given circle and we want to know what's its contribution to the total perimeter. So let's say we have several segments. So let's think about it in a simpler version. Let's say it wasn't a circle, but it was like a line, and we have several intervals that are erased. And we want to know what's the length of the part that's not erased. So just keep in mind that we can't say the total length of all, like the total length minus the sum of lengths of all the segments, because they can overlap. So on a line segment, this can be done by sorting all of the events. So let's say we know of all of these events. And so let's scan it from left to right. And we'll keep track of how many segments are being covered by a given point. So like there's no events so far, so it's 0, 0, 0. Then we come across this event and it's the start of a segment. So then we add 1 at this event. So now we have 1, 1. So then now the segment ends, so we have -1. So now, so like we subtract 1. So now we're at 0 again. So we had 1, we subtract 1, and we're at 0. Then again, we're at 1. Then we're at +2. Like this adds another 1, so we're at 2. Subtracts 1, we're at 1 again. Subtracts 1, now we're at 0. So if we know the times of all of the events, we can say for each time we're at 0, take the length until the next event. Every time we get 0, and we'll assume that like the start and end are events of +0. So just by sorting, we can solve the problem for a line segment without too much trouble. So you just sort the intervals and scan it. And we have a bunch of segments and like the number of segments, like the number of segments covering like each of these intervals. And we just need to sum all of the ones that are zeros. So that's the solution to if we had it on a line, but we don't have it on a line, we have it on a circle. Now, it's not too hard to do it on a circle once you know how to do it online, because you can just say, let's just cut the circle at the x-axis. So we will just consider this as one line segment. And then we will, so consider a segment that could be covering this. If it's like this, then it's perfectly fine. Like we just take the two angles and they create a segment. The issue happens when we have some segment that crosses the x-axis here. And we can handle that by splitting it into two segments, one from angle 0 to say alpha, and then another segment from this angle beta to 2 pi. So like we cut the circle at this point and then sort of lay it flat is how you can imagine it, and it reduces directly to what we already solved on the interval. So like we could have a segment that becomes two segments, but other than that, it's just an interval problem. So now how to compute for two circles their 2 points of intersection, and how to know, given the 2 points, which side of the circle is the actual part being erased. So you can compute the intersection points using a template. So in ICPC, you're allowed to use template code, and there's a popular template called KACTL. I use their circle intersection code. You can also refer to it for lots of different common standard algorithms if you don't know how to code a lot of them. But for in their geometry section, they have a circle intersection. So it will detect different cases of. So it's pretty tricky because there's several cases, like what if a circle is contained inside of another circle? What if the two circles are separate? What if they're exactly tangent? What if a circle Like what if it looks like this? So this is a case where like the segment that's being erased is actually most of the circle. So it's not correct to say consider the two intersection points and take the smaller of these two segments. Okay, so let's suppose we take the two circle intersection points from our library, whatever one you use. It's actually programmed in such a way that the two intersections come in a correct order to determine the segment. So like let's say the two intersection points are A and B. The code will give them to you in an order so that, I forget which orientation, but let's say it's always that you take A and then you go counterclockwise until point B, and then that's the segment you want. So the template code will always give it to you in like a consistent orientation to get that segment. I guess something I skipped over is once you know the segment, how do you get the angles of the two events? To get from a point to the angle, you take like the difference of these 2 points is a vector. And there's a function atan2. And you can give it, so like let's say this vector is xy. You can call atan2 of yx, and then it tells you the angle from the x-axis of that vector. And I think it's in the range minus pi to pi. So you can adjust it to be within 0 to 2 pi if you prefer. Are there any questions about this?
So I saw you did a few submissions. So what was the issue in the earlier submissions?
One issue I had was I had an incorrect circle intersection. I thought I was better than the library. And it turned out my code like divided by 0.
Oh, I see.
I copied KCTL code. What was the second error? Okay, I think the second error was that I assumed atan2 returns the angle within 0 to 2 pi.
I see.
But it actually returns in the range minus pi to pi. So those are my 2 errors.
Okay, cool.
Other common errors would be like things with precision, like if there are 2 circles exactly at the same center and radius, then you need to make sure that you count the second circle as covering the first circle. So those are things to keep in mind and are often like issues with geometry problems to think about. Should we move on to G?
Sure.
Okay. In problem G, there's a bunch of houses in a row. Each house has a height hi, and so the following process happens. As long as there's a house that's below this number, then it should be increased. Its height should be like increased to that value. So what exactly is that value? Like let's say we have hi minus 1 and hi plus 1. So the condition is that it should be it's bad if a house is the average of the 2 neighboring houses minus k, or was it plus k? Plus k. So basically we always want a house to be at least the average of its neighbors plus k. And as long as that condition is not held, then we should increase it. And the question is, given the initial house heights and the parameter k, if you keep on doing that process of increasing houses while they don't meet the condition, the statement says that they can show that it will end in a unique like list of heights, and it will stop. And the question is, what's the tallest house after that process is done? So like, let's say we have these houses. We have like 39, 10, and 40. The houses, like the first and last houses, will always stay the same because they don't have a house to their other side. So the average of this is 39.5. K was 1, so then this point is 40.5. So the second house will be increased to that amount. And then the process stops here because the condition's met. And the tallest house has height 40.5 at the end. So this is the problem. There's something really annoying where they give it as real numbers, like up to 10 to the 20, and I think that was the reason I failed it. Like I had the correct solution idea, but it was this thing that killed me with not enough time to fix. But let's think about the actual problem. What I noticed from the problem statement is that the condition of like a house being at least the problem of it being at least the average is actually like a convex property. So like if we let's say we ignore the plus k, then actually the like saying it's above the average means that the curve of points and houses would be concave. It's like it would be like this. So if you connect two houses, then it's above the average. Like any line segment is below the curve. So the question is, how do we like this convex property? If we asked about if we just asked about that, like if k was 0, then the problem is pretty simple because there's convex hole. You can you take the convex hole of the sets of houses if you plot like IHI. And then every house will end up like at the line segment above it. So that would be the solution if k was equal to 0. But the problem is it's not 0, it's plus k. And how do we handle that? So what I thought from this point was maybe it's not convex hole of IHI, but maybe if the points were transformed somewhat, then the problem actually is convex hole because the condition is very similar to it. And in fact, let's suppose that the points are transformed somewhat. Let's say that instead of IHI, we make the y coordinate we shift it by some function of I. I don't know what this function is yet, but we'll see what it should, like if there is such a function that will turn it into convex hole. So I will call this xi. So what we should want is to transform the points so that the condition is exactly convex hole of these points on xi. Maybe I shouldn't call it x. Let's call it like Let's call it y because it's the second coordinate. So let's just see if we can make it work. So we'll take, so what we want to hold is yi greater than or equal to yi minus 1 plus yi plus 1 over 2. Exactly. So I'll just multiply it like this. So let's see. All right, maybe I should do a reversed. Yeah, I think I'll do this reversed. So like the condition is hi greater than or equal to average of these plus k. I'm just going to multiply by 2. And then let's write hi in terms of yi. So we have 2 y minus f. That should be minus. Okay. So like we have this equation that we want. However, we want the condition to hold for yi. So we can actually ignore those. Or we have a 2 here. So we actually have like a recurrence for f. So basically we can use this equation to solve for this function f of I for all I. Then we have these points I, yi. Then it becomes, the problem exactly becomes compute convex hull of those sets of points, or that set of points. Then each point, like at the end of the process, it will become the point on the line segment above it in the convex hull. Then we will adjust again by f of I, like to undo that, to get its true height. So essentially the point, so in summary, the algorithm is adjust the points like by increasing the y coordinate by this function f of I, compute convex hull for each point, take its point on the line segment above it, convert it back to height by subtracting f of I. And then now we have the heights at the end of the process. So we just take the maximum one for the answer. It's kind of confusing, maybe.
Yeah, so I know the without the k0 it will be convex hull, and then also I guess without if all the house start with the same height, then it's the recurrence part. So I guess a key observation is that the problem can be solved by solving the two steps separately. So.
Yeah. Like it's kind of solved by just sort of a hunch that like this condition is very close to convex hull. So how can we like what if we tried to force it? Can we? And then the answer is yes.
So the solution to that recurrent, is it linear or exponential?
I believe I solved it exactly instead of like coding the recurrence.
I see.
And I think it was like 2ki times I plus 1.
Okay. Oh, so it's quadratic. Okay. I see.
So, I mean, after all of this, like my main problem was just, I think like precision errors, and I didn't fix it. But
is the I the smaller of the to the boundary, or it should be? Or is it actually always increasing, or at some point, or this thing is also kind of
I don't understand.
So is the I is the number of the point from the left, or
yeah, it's the index. So like there's.
But so it's always increasing. You don't decrease toward the end, or shouldn't the middle be highest? Or if you have this 6 point,
I'm sorry. I guess I'm not understanding. Like
so just in this case, suppose there are this 6 point, then
okay. Like suppose all the heights are the same.
Yeah, so you will have this.
Yeah. So then like I will take the convex hull of like it would. I guess it would look quadratic. Something like this. The convex hull would be this line segment. Everything would be mapped to this line segment.
Right. I guess I'm just wondering, this part is actually quadratic, keep increasing, so you don't actually decrease toward the end. So you have a dome shape instead of just going up quadratic curve. So I guess intuitively I was expecting like a dome shape.
So like in this set of transformed points, I'm not really sure what it would look like. I guess I guess in order for it to curve down, like these heights would have to be extremely low. But the thing is, like the points in this transform space, we undo the quadratic part. So it actually would end up with something in the middle, I think, if the heights were the same.
Okay.
Like the points at the end don't travel as much, or maybe it's not very intuitive. I guess it's like I travel up this much, but then I undo like this increase. So actually, like the height isn't very high. It's kind of hard to think about, actually.
Okay, that's fine.
But yeah, it still justifies, like in this case, then the tallest house at the end would be somewhere in the middle.
Tron, do you have things to add?
No, I don't have anything.
Oh, okay. Cool. Thank you.
Yeah.
Mm-hmm.